Okay, so our talk is about an alternative approach for discovering relationship between bacteriophages and antimicrobial resistance. And this work is a joint work with a number of people, including Maya Zelaskova and Dimitar Vasilev from Sofia University. As you mentioned, Dimitar Vasilev is associated with CAMDA for a number of years, and so he's kind of the leader of our project. This particular this particular talk is and work was associated with CAMDA 2021. And the main goal of MetaSup and CAMDA for this year in particular is to explore systematically the coevolution of the bacteria and their corresponding phages, and to potentially be able to predict antimicrobial resistance events from sample collected in strategic monitoring areas. Also to understand the relationship between viruses and their host, and in order to determine if antimicrobial resistance indeed can spread through phages. So this is kind of the two main goals. So the CAMDA challenge in particular had 4 specific tasks. The first one was discovery of phages in metagenomic samples with relevance to antimicrobial resistance. The second one was establishing species that may be infected by detected phages and also horizontal gene transfers. The third one was advancement of algorithms for the identification and discovery of phages and prophages from bacterial genomes, and in particular assessment of novel algorithms. And the last one was application and assessment of relationship mining for the occurrence of phages and bacteria in the context of antimicrobial resistance. We didn't cover all of the topics, the one in bold or the one that we tried to access and basically work on it. So I'm going to cover them. So there exists a number of research studies which basically confirm or questions the role of the phages in dissemination of antimicrobial resistant genes. And major objective, as we said, of CAMDA challenge is to acquire more knowledge about the relationship between viruses, hosts, and antimicrobial resistant genes in determining if antimicrobial resistance indeed can spread through phages. So this study is focused on discovering such relationship and possible dependencies between bacteriophages and antimicrobial resistance. The data were, as we said, collected from all over the world. And our approach is combination of different methods. We'll go over each method separately. This includes differential abundance of phages, diversity across samples, impact of antimicrobial resistant categories, and association with specific antimicrobial resistant genes. And also we used Bayesian spatial model in order to test some relationship between phages, host, and antimicrobial resistance. So the 4 different approaches in our study are the following. So we use compositional data analysis to find specific phages that separate samples based on their antimicrobial resistance profiles. We calculate different alpha diversity measures and compare them across different categories, antimicrobial resistant category. We also use Penalized Lasso regression to find best predictor models for antimicrobial resistance and also to predict continents and basically origin of the samples. And finally, we use Bayesian spatial models to estimate relative risk of phages by taking into account their host abundances. So this is kind of 4 different approaches with the main goal to investigate the relationship between the phages, host bacteria, and antimicrobial resistance. So this is kind of representation of what we have done. So this is a schematic representation. So we start with the AMR category, which we'll talk about. This is basically the data were provided by the samples were divided into groups, the high AMR group and the low AMR group. And we basically had four different type of analysis, as we mentioned in the previous slide: the composition, no differential abundance, the which is here, the alpha and beta diversity, the Lasso penalized regression, and finally we introduced some additional we introduced additional Bayesian spatial analysis in order to incorporate the spatial information which is given from the samples, and also to investigate the relationship specifically between phages, the host bacteria, and antimicrobial resistance. CAMDA challenge provides a set of samples, 124 samples from subway and urban public transport across all continents, and they're divided into two groups based on their antimicrobial resistant profiles. We have 62 high and 62 low AMR. This basically is like if the sample have a number of the counts of antimicrobial resistant genes are high above some threshold, the sample is classified as high, and so otherwise low. So each continent is represented by at least one city. Operational taxonomic units, counts of phages normalized as reads per million, were extracted from the samples using Hokkaido metagenomic classifier with NCBI database. The viruses database is the NCBI database. And the classifier uses protein level classification and achieves high sensitivity. So the total number of non-zero abundant viruses is about 6,000, while the total number of non-zero abundant phages is about 2,600. And we also extracted bacteria taxa using Progenome's database and summarized the counts on the level of species. So this was important because we used the host bacteria from here. And AMR profiles were actually provided by CAMDA and Pangea. So we actually downloaded this data. They're normalized. And this is different sets of antimicrobial resistant genes. So this is about the data. And so next, as we said, we start to apply 4 different approaches. The first one is the compositional data. So the compositional data approach is based on the concept of compositional data, which are vectors of non-negative components, which show relative weight or importance of a set of parts in a total. So we basically cannot interpret parts isolated from the others. And the data represented as a simplex, which is described mathematically here. And this is very commonly used with metagenomics data and some other data, of course, for which we have some proportions or counts. So the compositional data have different algorithms, and many of them are actually implemented in the R packages. So it's very convenient and very useful. So there's different geometry, data transformations. We also have a different algorithm for principal component analysis, algorithm for clustering, and so on. So this is, as I said, very useful because many of these things are already implemented in R, so we could use them directly. So the metagenomic data in particular are compositional data, since some of our component values depend on the sampling procedure and also the data are proportional. And so if we take into account this structure, we could perform a differential abundant analysis using these compositional methods. Basically, we have 2 categories, high and low AMR, and we want to compare the phage abundances for high and low AMR and find for which phages there is a difference between the 2 groups. So we used the R package ALGX2, which was developed using Bayesian methods for detecting an overtype of differential expressions. And finally, we also use Fisher exact test to find possible overrepresentations. So from the discovered differentially abundant phages, we want to find which group or which family is overrepresented. So the results of this analysis leads to 136 phages, which differentiate the two groups, high and low MR. As I said, these groups were set by the relative antimicrobial resistant counts and were done by, could be downloaded, the actual data from Pangea. 114 of them have significantly higher abundance by FDR, adjusted by FDR, in the high IMR group, and 22 have significantly lower abundance in the same high IMR group. So the next slide shows two heat maps that shows the distribution of those phages across the continent. And the Fisher exactas also, the abundances were pooled by phages, so they're grouped by phages, and by phage families, sorry. And Fisher exactas show that this Myovirida family is overrepresented in the group of differentially abundant phages. So here we have these two heat maps. The first one is the scale data. So we see clearly the green one is the low MR, the red one is the high MR. So we see that this particular 130 phages combined by their families differentiate the two groups. Also on the bottom is the actual abundance, non-scale. So we could see that the classes Myovirida and Siphoviridae, sorry, the pronunciation is probably wrong, are overrepresented. And Myovirida in particular is overrepresented. So, I mean, these two have a high abundance, but the Myovirida is overrepresented. So this was the first part, the compositional differential abundance. The second one is we try to use some diversity measures like alpha and beta diversity measures to characterize, to find if there is differences in the IMR category and also among continents. So the alpha diversity is variation of microbes in a single sample, and we use 3 indexes. Of course, there are a lot more, but we focus on those 3. So the Chow index is, these are all the formulas. So the Chow index is based on the number of observed species and the number of singleton and number of doubleton taxa. The Shannon-Wiener index is based on the information criteria using the like the entropy proportion of individuals of species I. And the Simpson index is just 1 minus these squared proportions. So each of these indexes has a different impact. So the Chow index is skewed towards the rare units. The Shannon-Wiener index have also importance to less common, but the Simpson index give more importance to more common species. So if we use all these 3 indexes and compute the entropy, so we divide it by the 2 groups. So we have alpha diversity measures for the high and low MR and also among continents. So we see some differences. So for example, the low MR has a much smaller, deviation. So but most of the samples are actually clustered together. So the green one, the red one has a lot more samples that are more broadly broadly distributed. We also see some differences, like for example, South America has a high diversity. Oceania, for example, has a low diversity. This is in purple. Of course, based on these graphics, we cannot, I mean, we see visually, but we also performed some statistics in order to show if there is differences. And in this particular case, the Kruskal-Wallis test shows that there is a difference between the samples, between the 2 different categories, and for Chow and Shannon. And for Simpson index, it was a borderline, so the p-value was a little bit high. Also, if we do the same thing for continents, again, we see differences, especially with South America. South America shows the highest diversity, and it's very different than the others. Okay, so next one is the beta diversity, which is the variation of microbial communities between samples. And there's different measures. Binary similarity is usually used by Jacquard or Sorensen indices. In this case, we use Bray-Curtis. This is just the formula for it. It's the number of individuals in species I for each pair of samples, JK. So it's just the difference over the sum of the species. So this Bray-Curtis index can be used in analysis of principal coordinates like a PCA type for compositional data. So we basically plot the first two coordinates, and we see that clear distinction between low AMR and high AMR, and also we see distinction between the continents. So here, of course, the data are the phages, the bacteriophages. Here we see Africa and Oceania are kind of distinct from South America, North America, which are more close together. And Asia is also distinct from the others. It overlaps with Europe though. So, the constraint analysis of principal coordinate using this Bray-Curtis dissimilarity shows that there is clear differentiation between the low and high AMR samples. So the phages differentiate them. And also within the continents, Africa and Oceania phages profiles are more distinct than the others. And we use this permutational MANOVA in R with this particular function for 1000 permutations, and the p-value shows significance for both of the effects on AMR category and continents. So again, we see differences that the phages actually are, the profiles of phages are different between the categories. So the third part of the analysis is the so-called Lasso penalized regression. And this is usually very commonly used for feature selection and for prediction. So this is in this study we try to apply several models, but we focus primarily on the Lasso regression, the penalized Lasso regression, which is a regularization technique that achieves accurate prediction by avoiding the overfitting of the data. And in this particular implementation, we use the phages data to predict the variation within a sample and basically to predict the two classes, the high and low AMR. We also use to predict continents. So this is just the standard. I think we took these slides from, it's a standard slide for the least absolute, the Lasso, which is least absolute shrinkage and selection operator method. It's a penalized regression that simultaneously performs variable selection and also regularization. Basically, it's a minimization of the error plus some penalty term, which is multiplied by the weight parameter, lambda. And this is all the P predictors, and the response is Y. So using this penalty term. Based on this Lasso, which is also, as I said, implemented in the carrot package R, we select phages that differentiate the two categories, and we achieve high sensitivity and specificity. The top feature are basically from these two major families, Tamioviridae and Siphoviridae. And this is the list of the top features that differentiate between the two categories. If we apply the same method but use the continents as our response, we also get a good prediction. And here is just the example of some of the top features that are that predicts the continent memberships. This, I think, is the log counts. So we see some Africa and Oceania again have some of the highest counts in this particular for these particular features. Okay, So finally, we are going to focus on the part that is kind of maybe more interesting, the Bayesian spatial analysis that tries to incorporate spatial information and phage abundance, bacteria abundance, and AMR, antimicrobial resistance, and tries to estimate the relative risk. So this method is generally used in disease mapping, and we thought that it's relevant here because we basically have a phage or virus and a host, which is in this case bacteria. So the idea is the following. So there is a debate: is there how the antimicrobial resistance happens, and is there association between the phages and antimicrobial resistance? Are they causing antimicrobial resistance? And so there are two types of transmission. One is the bacterial transduction, and basically we have a phage and we have a release of the phage, and then the corresponding antimicrobial resistant genes can be transferred to the bacteria. And the other, of course, is just the bacterial conjugation, where we have a just transfer between the bacteria without any phage involvement. So it may be difficult to differentiate this. For some bacteria or phages, some of the situation may be more relevant, for others, the other. So the Bayesian spatial model is something that we try to see if we could differentiate these two cases. So if we could basically say what we have, one or the other. The Bayesian approach, as I said, is very commonly used when there is a spatial autocorrelation. And spatial autocorrelation is in general common when observations that are close in space also have similar values. And previous studies, and we also applied this method in previous CAMDA challenges, we observed that there is a spatial correlation between the samples. And proportion of this spatial autocorrelation is usually modeled by covariates, but not always. It's possible to do that. And some of these correlations still remain in the residues. So the spatial models, such as Bayesian hierarchical models, are usually used to augment linear predictors with a set of spatially autocorrelated random effects. And usually these random effects are represented with a conditional autoregressive priors, and they're just included in the model. So it's actually, we'll see in the equation later on. In particular, we are going to use the Bayesian convolution model called Besac-York-Mollier. It's a convolution model with conditional autoregressive prior, Poisson likelihoods that contain both spatially autocorrelated and independent random effects. And the response also is assumed to follow Poisson distribution, and it counts for overdispersion, which is common in metagenomics data. And the main sort of variables in the model, these are observed, which is in this case the phages, expected, which in this case is bacteria host, and theta is the relative risk, which basically is the ratio between the observed and expected. So, okay, so the relative risk is the posterior estimation of the C ratio, which is actually observed versus expected. So this is going to be our main variable in the model. And then we are going to estimate, and the estimator, the posterior estimate are going to be interpreted as a relative risk. So observed is going to be basically the phage abundance or the counts. The expected are going to be proportional of abundance of a host bacteria. This actually is analogous to disease mapping. Basically, we have a virus and a population. So expected is basically proportional to the population. So this is what we kind of were thinking, that this is a similar situation, and that's why this model is relevant. So the actual equations are the following. So we have, as I said, this is the observed versus expected, or theta, which is the ratio, and it's a Poisson. And basically, this means that the logarithm of theta is a linear model like this. X is a matrix of covariates. Beta is the vector of regression coefficients. And the two, V and U, are actually the random effects. One is a spatially unstructured random effects, which is V. And U is actually the spatial autocorrelation. So here is where we include this neighboring matrix W, which is based on the latitude and longitude. And so we just calculate the distance between the samples, and we could discretize it, make it binary based on some threshold, or we could use the distance by itself. So using this model, we estimate the relative risk of bacteriophages. So here, as we said, the observed is the bacteriophages. The expected is the host bacteria, proportional to the host bacteria. So we want to estimate the relative risk, and we include in the model the AMR category. So here in the covariates, we include the two groups, the high AMR and low AMR. This is our covariate. So we want to test the effect of AMR on the relative risk. So the idea is that if the phages relative risk is higher than 1, and the AMR category credible set, this is like a confidence set for the Bayesian model, does not include 0, which means that AMR category has effect on the phage relative risk. This just means that the phage abundance is higher than what would expect based on the host bacteria, just more abundant than what we expect. And this higher risk can be partially explained by the covariate, which in this case is antimicrobial category status. For example, one AMR group has an increased risk, while the other group has a decreased risk. So this is something that we want to find. We want to find for which phages or bacteria, which situation do we have. So in this particular example, we took Salmonella enterica and Staphylococcus aureus, and then we used this database. And what we did is basically query phages bacteria pairs. So from this database, we query all these multiple pairs, because sometimes a single phage can infect multiple bacteria, and a single bacterium is infected by multiple phages. So, and then we kind of accumulate. And so on one side, we have the phages, and on the other side, we have bacteria. And then we use the bacteria, the abundance of these bacteria, to calculate the expected. And then observe this, of course, the observed counts from the phages. And so this may be a little bit too many graphs, but I'll go into details in each of the. So let's start with this Salmonella enterica, because it's probably the simplest one. So here is, we have the Salmonella enterica related phages. As I said, we go here and query. So which are the phages that are infecting the Salmonella enterica, and then we get this list of these phages. We get their abundance, and then we feed the model using the Salmonella enterica as expected abundance. And then what we get is that this is log relative risk. So basically we get that we don't have any difference in the categories. We don't have any difference in the continents, and the relative risk is basically not very high. So it means that basically the phages are proportional, and they're what we expect. If we have a Salmonella enterica, all the phages that infect Salmonella enterica, they're just, of course, proportional to the amount of Salmonella. So there's nothing really special. However, if we take the Staphylococcus aureus, what we observe is that in some cases, like in Africa, for example, we have a larger relative risk, which means that we have more phages than the actual bacteria. And we also observe some interesting in South America that in antimicrobial resistant areas, which are in red are high MR and green is low MR, again, we have an increased risk, basically more phages than what is expected based on the host bacteria. This is with the Staphylococcus. However, as I said before, Staphylococcus aureus, there's several phages that actually attack other bacteria as well. So if we combined and we created these pairs, we end up with the second graph, which is right here, which is combination of the two bacteria, because there are multiple phages that attack both. And in this case, of course, the risk goes down and becomes pretty much like the Salmonella. However, we see still very interestingly that in South America, still the red one, which is the high MR, still have a high risk. So we still have unaccounted, so to say, so phages that are in more abundance than what is expected. So there is some caveat, of course, here is because we use this database and we rely on this relationship, but this database may be not complete. So it's possible there is other phages that infect Staphylococcus aureus, and also maybe these phages infect other bacteria as well. So this is something that we want to pursue to find a larger maybe database that has a more complete relationship between the bacteria and the host bacteria and the phages. So we could just rerun this analysis and see if we keep these results. But it based on this, it shows that definitely there is some connection between the antimicrobial resistance. So in this particular case, maybe there is some connection between this antimicrobial resistance and the phages, the relative risk, because this is what the model will show, that this relative risk is actually influenced by the antimicrobial resistance. So there's some, as I said, caveats and some remarks about this spatial model. So we have a small sample size with available spatial information for some of the continents like Europe, Oceania, and Middle East. So we need to get more data to confirm and to extend this model. Also, this model may be more useful when we have closely related municipalities and cities. So we can actually track how phages evolve and if their relative risk changes across borders. And as I said, similar to the disease mapping, we need more larger and maybe more complete database that lists all the corresponding phage host bacteria in order to put them into the model. And of course, we need a number of covariates. Like we use category only, but there may be other things that actually influence the relative risk, like the climate conditions and many others. So this is something that we want to pursue to include more covariates. So finally, the final part of the analysis is we want to investigate the correlation or relationship between phages and particular genes, antimicrobial resistant genes. So recent studies, strange from 2000, this year actually, analyzed the global and regional distributions of phages and their impact on transmission of antimicrobial resistant genes between bacteria. And he found their group found significant correlation between phages and antimicrobial resistance genes. And of course, due to the low abundance, we also observed that we have a low abundance of phages in general. And these studies, more studies are needed in order to confirm this, but we also observed the same correlation, we'll show you later. And some of the findings also indicate that phages in sewage, for example, are widely distributed as free-living phages, not always associated with bacteria and persisting longer than their host. Okay. Again, as we observe that we again in this graph here, we observe that in some cases we have more phages than the corresponding bacteria. So this might actually confirm what they also observed. Okay, so hello. Oh, I don't know.
Yes. No, here everything is fine. I
Yeah.
mean,
Okay. Yes, I hear some. I don't know if from where, but there is some noise. So anyway, as I said, we also discovered these associations, and these associations basically are also highly. I mean, the phages and antimicrobial resistant genes are highly correlated. And we observed two major biclusters. One is a bicluster that involved these genes, RCB, PAR-E, RPOB, and TUF-AB. They are mostly correlated with the mu-viridae phage family. And the other cluster is genes are BLAST-Z, ARM-X, and others. They are mostly correlated with the Cyphoridae family. And the phages in one cluster are negatively correlated with the antimicrobial resistant genes from the other cluster. So here is the example. So here in the big one is the mu-viridae group. On the x-axis is the genes, and here is the corresponding phages. They are mostly in blue, which is the mu-viridae. And the other cluster is this, the smaller one. These are the genes in the smaller cluster, and they are correlated with the other one, the Cyphoridae. And as I said, they are negatively correlated, the two clusters. So basically, the conclusions from this work, so this is kind of preliminary still we are trying to write the paper right now. So the major conclusions from this work is that based on our main goal was to, and the main goal of the challenge was to study the relationship between bacteriophages and antimicrobial resistance. And based on the 4 different analyses that we perform, we, based on the compositional differential abundant analysis, we found that phages which differentiate the category, we found these phages, and also we found that they are highly correlated. The phages also are highly correlated with antimicrobial resistant genes, which are in general overrepresented by the mu-viridae family. Also, diversity measures differentiate between the category and the continent, and we observe differences in, like South America, for example, have a highest diversity index. Oceania was among the continents with lowest diversity index. Again, some caveats here that we may need more samples since we have few samples for some continents to confirm these findings. Also, top features selected by lasso regression achieve very high separation for the IMR categories as well as the continents. And finally, the Bayesian spatial analysis may be helpful to examine how the phages evolve across spatially correlated samples, and in particular, to estimate the relative risk, including the host bacteria, and see if we could differentiate, basically see if we could say which scenario we have, that phages are antimicrobial resistant has an impact on the relative risk of the bacteriophages. So the future directions, there are a few things that we could do. For example, we could use larger databases for viruses. Currently, we use NCBI. And we also could use a larger database for bacteria, so we could find more host bacteria. Of course, we could use more sample. Right now, the design is balanced with respect to low and high MR, but it's not balanced with respect to continents. So some continents have few samples, so it may need more in order, for example, to test if there is some interactions between the different category and continent and geographical locations. Interestingly, it's like in this, So here we found these correlations, but it would be nice to see if we could try to find some sort of a biclicks. In other words, this type of pairs between phages and particularly some specific antimicrobial resistant genes. Also, we want to include more relevant covariates in the Bayesian model. Right now, so we use only the category, and some additional ways to define the expected. Currently, we define it as a proportional to the host bacteria, but some more biological relevant may be also used. Okay, so as I said, there's a number of co-authors for this work. I already mentioned Maja Laskova and Dimitar Vasiliev. We also have Ilian Mikhailov from Sofia University, Stefan Tsona from Agrobio Institute in Bulgaria, Miroslav Zoric from let me just say it's Institute of Food and Vegetable Crops from Novi Sad, Serbia. Stefan Kirov, who is like my former colleague from Bristol Myers Squibb, David Danko and Christopher Mason from Weill Cornell Medical College in New York. And that's basically it. So here is the references. There's multiple things that we used here that are so basically investigate the correlation between bacteriophages and antimicrobial resistant genes. Okay. And so I just want to thank again, thanks to Metasub and CAMDA for providing all the data and organizing all of these events, Sofia University, and also thank you for all of you for your attention and attending this lecture. And I appreciate all the comments, ideas, and questions. Thank you.
So, thank you. It was really entertaining talk. I mean, it's a really nice connection on both the background math, but also the understanding what's going on. I know it's difficult.
We try to do some work interpretation. So
I was thinking about this additional covariate which you have mentioned. I think that the one which might be the most informative would be the antibiotics usage in different countries and cities.
Yeah, we were thinking about that, but I was not sure which database we need to use.
Yeah, I think it might be difficult because the ones which is used, let's say, for human treatment might be still available, but we have to remember that a huge probably the source of the resistance and the source where the antibiotics are used is the farming, right? When we have the cattle, so we have the pigs and everything. So and this probably might be way more difficult to trace. So, but definitely this is something which is a source of the.
Even in the previous CAMDA project, we were thinking to use this, but we couldn't find some kind of complete database.
Yeah, exactly. So they might be extremely informative, but if they would be complete, and we know that the completeness might be a big problem. So in the chat there are questions from Michał. So I will start one which is on the top. Is construction of artificial categories such as transposable fakes based on the transposase occurrence within metagenomic samples could increase the information, or it could create just noise and it's basically cleverer to rely on databases?
Artificial categories such as transposable phages based on the transpose occurrence within metagenomic. I'm not really sure I understand that very well.
I don't know whether the audience can also talk or they can only ask questions in chat.
Yeah, I don't know. I'm not sure.
The Q&A is the only option, unfortunately.
Okay, so maybe Michał, I will read the second question and you maybe will rephrase the first one. So the second question is having in mind that fake databases are a bit biased towards really similar caudovirals these days. How do you think this situation affects your solution?
Yeah, that's true. I mean, yeah, that's true. We used the phage data from NCBI, so I read few papers that they compare the databases from different sources, and actually there is a more complete database. So definitely we probably will not find there are some phages maybe where will not discover all of them. So definitely there is, it probably biased towards specific families and things like this. I mean, in general, for I think for the Bayesian stuff, because we focus on a specific phage, so it's possible that maybe there is more phages in the same class that we don't find. So it's again, it's not complete. So maybe will change. I don't think that will change that much of the correlations and all of the things that we find, but it may move the focus to some of the other families, basically. So, but I think that still the idea of, especially for the Bayesian, I think it's very relevant, and probably it's going to change, of course. Like we saw, if we have if we use the pair of phages, like more phages that attack, I mean, more bacteria, so then the model, of course, changes, the result change, because it adjusts for the expected value. So definitely will change, but I think that the general correlation of antimicrobial genes with phages will still remain. I mean, we definitely observe this in the data.
Okay. Michał has provided some explanation that in fact these two questions are somehow related. So I think now it's a bit more clear. I mean, that we know that the databases are not complete, and the question is whether it's better to create artificial categories or maybe still use the database knowing that it's not complete, because as Michał rightly says, that creating some artificial categories might just collect noise, and then it will not be, whether it will be informative or not.
I don't know. I really don't have much experience with that, so I don't know.
I mean, I think it's quite common problem in general in metagenomics, let's say, because all this, also the bacterial databases are far from being complete. Yeah, I think, but still probably with the fakes and with the viruses, it's even worse. I think in the last in the last paper by Metasub Consortium, we shown we've added some new bacteria to the databases, but proportionally way more was the viruses and the fakes. So I think this is where it's still a lot needs to be done. And as you say, you'd like to have also more samples that they are denser in the closer cities. So we are working on it.
Because the model will be very useful when we have a lot more, like we get the boundaries and see where the things change, when the relative risk changes between. Right now, we don't have that many samples in each particular one. So,
I mean, the concept for this challenge was to do some kind of the exploration whether the field has a potential, and based off what you and the others from your team you did, seems that there's a lot of potential, and now it's just the questions which direction to go, from where to obtain the data, and how to best structure it for the future. But I think we have learned a lot from your research, and then now we have some kind of the idea which direction we should go with the further challenges.